So today we'll do a new topic which is center of mass. Center of mass. Very important chapter because if you want to do rotation or collisions or more advanced topics, this is a must. So let us try to understand this. Center of mass is a point, or I can say location, okay, for a group of particles or a body. For a group of particles or for a body. Why we are interested in this point, that we will learn slightly later. What is the advantage of knowing center of mass and how it will help us in dealing with very complex motions, all that we will see later. But first, center of mass, the name itself says center of mass. So there is an object or group of objects which are there, and I am trying to find this point or this location which I call as center of mass. So how is it calculated? So let me just get into the definition first. In order to first calculate center of mass, you need a coordinate system. You need a coordinate system to calculate center of mass. So suppose I have a coordinate system. So my x and y axis are there. Z axis also may be there. And I want to tell the coordinates of this special point called center of mass. What do I have? I have a mass, let me say m1, whose position vector is r1. What is position vector? The vector joining origin to the particle. So I have a particle of mass m1 whose position vector is r1. Suppose I have another particle m2 whose position vector is r2. I have yet another particle m3 whose position vector is r3, and so on. So I have many such particles and I know the position of each of these particles. When I say position vector, you should understand, suppose if I say r1, position vector of first particle, you can split it into components like x1i plus y1j plus z1k. You can write like this, or you can write it as x1 comma y1 comma z1. You can write it as a coordinate. So position could be written as a vector in the form of ijk, or position can be written as coordinates. If you, for example, look at 2D, suppose I have an xy plane, and suppose I have a particle at 2 comma 1. So that means you went 2 units on x-axis and you went 1 unit on y-axis. So this is 2y, this is 1j. When you add both, you get 2i plus 1j. 2i plus 1j. So the position of this particle, I can write it as 2i plus 1j, or you can even say it is 2 comma 1. So either you can write it as a coordinate or you can write it as a vector. So similarly here, I can write if needed r1 as x1i plus y1j plus z1k, r2 as x2i plus y2j plus z2k, and so on. So you have a choice to write them like that, or you can write x1, y1, z1 for this particle, x2, y2, z2 for this particle, and so on. So you have that flexibility. So I have this group of particles whose mass is known, whose location is known. Now I want to find the location or coordinates of this special point called center of mass. So how do I find it? So the definition goes like this. Position of center of mass, obviously from origin. Whenever I say position, or position vector, it is from origin. It is given by first mass multiplied by its position plus the second mass multiplied by its position. Like this, you add all terms. So each mass you are multiplying by its position, you are adding all those. Then you divide with total mass. So you divide with total mass, which is m1 plus m2 plus so on mn. This is how you calculate this coordinates of this special point called center of mass. So if you have a group of particles, take the first particle, find its mass, find its position, multiply both. Take the second particle, find its mass, find its position, multiply both. Like this, you multiply the mass with corresponding position, add all these vectors. Note that mass into position is another vector. Okay, if r1 is a position vector, when you multiply it with mass, it will change its length appropriately and becomes a new vector. So all these are vectors. So when you add them, you get a vector, and then you are dividing the vector with total mass to give another vector that we call as position of center of mass. You can write it in sigma notation, sigma miri by sigma mi. What is sigma notation? So whenever you write sigma of suppose xi, you start giving values to this I starting from 1, and then you give first 1, so it will become x1, then plus give next value to I, that is x2, plus x3, so on. So whenever you have sigma xi, that is interpreted as x1 plus x2 plus x3 and so on. So you give 1 to I, then put a plus sign, then give 2 to I, put a plus sign, give 3 to I, put a plus sign, and so on. So for example, if you do that here, first you give I as 1, so you get m1 r1, put a plus sign, then m2 r2, put a plus sign, then m3 r3. So you are giving values for I starts from 1 and goes all the way to as many particles are there in the system. Similarly, denominator will be m1 plus m2 plus m3, so on. So this is another way of writing the same thing. This is called sigma or summation notation, sigma notation we say, or summation notation. This I is called index of the summation. It starts from 1. Sometimes people write it I equal to 1 to n, like this they write on top and bottom of the sigma to clearly mention, because sometimes I can start from 0 also. So for example, here I can say I goes from 1 to n. Similarly, here I goes from 1 to n. So start with the lowest value of I, that is 1. When you put that, you will get m1 r1. Then put a plus sign, because sigma means plus addition. Then give next value to I, m2 r2 plus m3 r3 plus m4 r4 and so on. That is numerator. And denominator will be m1 plus m2 plus m3, so on. So this is how it is written. This is how you calculate center of mass position. So let me explain a bit more. Generally, whenever you have the positions of particles, r1 is the position of first particle, r2 is position of second particle. You see here, r2 is position of second particle. Similarly, r3 is position of third particle. Suppose you add all these positions and divide by the total number. This is called simple mean or simple average. This is called simple average. Simple average means you add all the quantities, divide by the number of those quantities. For example, if you have some 10 numbers, okay, 2, 8, 6, 9, 4, 5, 12, 13, 20, 80. Suppose you have these 10 numbers. What is the average? You add all of them, divide by the number of these numbers, which is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers are there. So we add and divide by 10. That is the simple average. Okay, that is the simple average. So similarly, if you take all these positions and add them and divide by the number of those positions, that becomes simple average. But center of mass is not simple average. It is much more complex. So how are we calculating center of mass? See what we are doing. You are not just adding R1 plus R2 plus R3 divided by n. Rather, you are multiplying each position with the mass that is located there. That means you are giving importance to a position based on the mass that is located there. If more mass is located at certain position, then that position is given greater importance. Giving importance is called giving weight or weightage. In your school, for example, or college, the teacher may give more weightage to you. That means more importance to you. You ask a doubt and the teacher will immediately respond to that doubt. Other students, no, let us say the teacher doesn't respond. So they are giving more importance or weight to you. Similarly, here mass is what determines the weightage of the position. If a particular position is more important, then there must be more mass at that location. So what you are doing, you are multiplying the position with the corresponding mass located there. Similarly, next position with corresponding mass and so on. And you are adding all these divided by total mass. So this is some kind of, or what we call as, mass weighted mean of position vectors. What is meant by mass weighted mean? It's a mean only, it's some kind of average, but not a simple average. You are giving importance to a position depending on what mass is there at that position. So you are multiplying the position with the mass present there. If more mass is present at a given location, that location will have lot of importance. If less mass is there in certain location, that location will have less importance. It will have importance but less. Like this, you are multiplying position with mass and adding all this by total mass. So it is some kind of average, but not a simple average. It is called weighted average. Weighted average means you will multiply position with weights or masses and by total mass. So that gives you center of mass. So center of mass is, I use the shortcut CM. CM refers to center of mass. Center of mass is mass weighted mean of position vectors. So you take a position, multiply it with the mass present there, you add all such contributions, divide by total mass. So ultimately you will get some position which you are calling as the position of center of mass. It's a coordinate, it's a point, it's a location, it's a position, center of mass. So our first 2-3 classes will be around the point how to calculate center of mass for different configurations. How to calculate center of mass if there are 2 particles, 3 particles, n particles. How to calculate center of mass of big bodies where there are infinite number of particles, like a triangular plate, a square plate, a rectangular plate, a circular plate or a sphere, a hollow sphere, solid sphere, cone. All these we will do. We'll find center of mass or this is special point for these different kinds of objects. So right now what I have given here is center of mass of what we call as discrete system of particles. Discrete system of particles. What does that mean? That means one particle is here, then there is a gap, another particle is somewhere else, then there is a gap, and so on. Suppose if I take an object, this has infinite number of particles. There is no gap also between particles. This particle, next particle, next. All these particles together make the object. This is not a discrete system. If you take an object like that, we call it as a continuous system of particles or an object basically. If you have a continuous system of particles, infinite number of particles packed together, it becomes an object, any object. So we have 2 kinds of systems. Discrete system, that means there are large gaps between the particles, and continuous system where it's an object with no gap between particles and infinite number of particles are there. So for discrete system, the definition of center of mass is what I have given here. M1R1 plus M2R2 so on up to MnRn by M1 plus M2 plus M3 so on up to Mn. Okay, this is for discrete system. In a discrete system, number of particles is finite. There are n particles. If you take a continuous system, the number of particles is infinite, so you can't add them like this. Rather, you have to integrate. So we will come to that. But before that, let us take this definition of center of mass and explore it more. So I wrote position of center of mass is sigma mi ri, that's like m1r1 plus m2r2 plus m3r3 so on, by total mass, which is sigma mi. This is the definition of center of mass. But as I said, we can write each of these vectors as components. So RCM I can write it as XCMI plus YCMJ plus ZCMK. Similarly, this numerator I can write as sigma. Instead of sigma, let me write completely M1 into X1I plus Y1J plus Z1K plus M2 into X2I plus Y2J plus Z2K, like this, Mn into Xni plus Ynj plus Znk by total mass, which is M1 plus M2 so on. So each of these positions for every particle I split into components: X component, Y component, Z component, or you could write them as coordinates also, it doesn't matter, we'll see that. Now we have an equation where I have ijk on left side also and on right side also. So whenever you have an equation with ijk on left side and ijk on right side, we can equate the I coefficients on both sides. Similarly, we can equate the j coefficients on both sides, and we can equate the k coefficient on both sides, because perpendicular directions are independent. For example, if I have ai plus bj is equal to ci plus bj, then compulsorily I must have a equal to c, okay, because j cannot affect I direction, and b equal to d, this you must have compulsorily. So if you have an equation involving ijk, we can equate the I components on both sides, because I components don't depend on j or k, because perpendicular directions are independent. So with that idea, I can equate the I component on left and right side, so that I get x coordinate of center of mass is m1 x1 plus m2 x2 so on mn xn by m1 plus m2 so on mn. This is x coordinate of center of mass. So if you want only x coordinate of this special point called center of mass, you can take x coordinate of every particle, multiply it with its corresponding mass, add all the terms, divide by total mass. Sometimes the total mass, sigma mi, which is m1 plus m2 so on up to mn, is written as capital M sometimes for convenience. Okay, the total mass sometimes is written like that. So I can write now xcm is sigma mi xi by sigma mi, or you can even write it as sigma mi xi by total mass m. Similarly, y coordinate of center of mass is given by sigma mi yi by m, or you can even write sigma mi also. And z coordinate of center of mass is sigma mi zi by total mass m. So this is how you calculate x coordinate of center of mass, y coordinate and z coordinate if needed. So let us see one example how to calculate the location of center of mass. Suppose, look at this example. Suppose I have a 2 kg particle and I have a 3 kg particle, and both are separated by 10 meters. I want to find where is the center of mass of the system. I want to locate this special point called center of mass. So how do we find it? Before you can find center of mass, you should have coordinate system. Here I can take the line joining 2 and 3 kg as x-axis like this, and y-axis is I can take here. Nothing wrong, you can take it anywhere, but I am taking in a most simplified way. So the 2 kg is at origin and 3 kg is at 10, 0. Let's find x coordinate of center of mass. m1 x1, that is 2 into its x coordinate is 0 plus 3 into its x coordinate is 10 by m1 plus m2, 2 plus 3. So it is 30 by 5 or 6. And y coordinate of center of mass is 2 into 0 plus 3 into 0, m1 y1 plus m2 y2 by m1 plus m2, that is 0. So ultimately center of mass is at 6, 0. So somewhere here. You can see center of mass is near to heavier object. Center of mass is near to heavier objects. If there are many heavy objects, it will be on that side. Suppose they are light and heavy objects in space. Center of mass will be nearer to heavy objects, farther from light objects. You can see here, center of mass is near to 3 kg, or it is far from 2 kg. Why like that? Because more the mass, more is the importance for the position. M1, R1. If M1 is more, you are giving more importance to R1. That way. Now one thing, the distance of center of mass from 2 kg is 6 meters. Distance of center of mass from 3 kg is 4 meters. Now let me tell you something very important. If you change coordinate system, the coordinates of 2 kg will change, coordinates of 3 kg will change, coordinates of center of mass will change, but distance of center of mass from 2 kg and 3 kg will not change, the physical location. So let me explain. This is 2 kg, this is 3 kg. Suppose if I took coordinate system somewhere here, distance between 2 and 3 kg is 10 meters, right? Suppose if I took coordinate system here, suppose the y coordinate is some y1, okay, and the x coordinate of 2 kg is, let us say, x1. So coordinates of 2 kg are x1 comma y1. Coordinates of 3 kg will be x1 plus 10 comma y1, because x coordinate increased by 10 meters. Okay. Now where is the y coordinate of center of mass? Y coordinate of center of mass is m1 y1 plus m2 y1, m2 y2. Y2 is also y1 only here. It's at the same height by m1 plus m2. It comes out to be y1 only. So center of mass y coordinate is y1, means it is at the same height. What about x coordinate? 2 into x1 plus 3 into x1 plus 10 by 2 plus 3, that is 5. That is x1 plus 6. That means it is here. X1 plus 6. This is x1. This is another 6. So you see what I am saying. The distance of center of mass from 2 kg is 6 unit. Distance of center of mass from 3 kg is 4. That did not change. Coordinates of center of mass changed, no doubt. But the physical location of center of mass, it is 6 meters from 2 kg and 4 meters from 3 kg here. That did not change. So depending on your coordinate system, depending on your coordinate system, the coordinates of center of mass will change. Coordinates of center of mass will change. But the physical location of center of mass will not change. Physical location of center of mass will not change. Let me explain this. Suppose right now you are in your house. That is the truth. You are in your house. Now I may draw a coordinate system with origin at you and say you are at origin. Or I may draw a coordinate system with origin at me and say you are at some xy. So depending on coordinate system, your coordinates will change, but the physical location that you are in your house will not change. Similarly, the center of mass coordinates may change depending on coordinate system, but it is between 2 and 3 kg and at a distance of 6 meter from 2 kg and 4 meter from 3 kg. That will not change. That is the absolute truth. If you take a different coordinate system, the coordinates will be different. But the physical location and its distance from 2 kg and 3 kg of center of mass, that will be fixed. That you should understand. So always whenever you want to find center of mass of a group of particles, first you should have some coordinate system. It doesn't matter what it is. Then you find coordinates of all these particles. Then what you should do? Multiply mass of the particle with the coordinates, add all such terms, divide by total mass. That will give you the location of this special point called center of mass. Okay, now what about center of mass of continuous objects, continuous system of particles? Up till now what we discussed is center of mass of discrete system. Discrete system means one particle is at one location, then there is a huge gap, another particle is at some other location, and so on. That is a discrete system. Okay, to give you an example, suppose there is one rice particle here, another rice particle here, another rice particle, another rice particle. It's a discrete system. You take many such rice particles and make it into a rice ball. Okay, you first mix it into a paste and make a rice ball. Now everywhere there are particles. There is no gap. This is called a continuous system. Okay, this is called a continuous system. So what is, how to find the center of mass of continuous system of objects? So let us see that. What is the idea? Suppose if I have some big object, so it consists of infinite number of particles, and I want to find center of mass of this. Now our traditional method is not easy. If you start chopping this object into particles, you will get infinite number of them, and then you got to do m1 r1 plus m2 r2 plus m3 r3, so on, m infinity r infinity by m1 plus m2 up to m infinity. It's impossible. Infinite terms, how to add? So we have to do some integration. So what we will do, first coordinate system should be there. So I've got my x-axis and I've got my y-axis. You take a small elemental mass which I call as dm. Okay, we will see how to take it as we do many problems in this chapter. We will for the first time possibly understand how to take an element and then how to do integrations and all that. This marks the beginning of this integration, how to take an element and how to integrate, and that will continue in later topics also. When we go to rotation, there we will calculate moment of inertia also in a similar manner. Right now we are calculating center of mass, there we will calculate moment of inertia, and going further this will continue in the second year topics also, electrostatics and all that. So now I took some arbitrary mass dm, point mass, I found its position, let's call it r. So what you got to do, you have to multiply the mass with corresponding position. So mass is dm, corresponding position is r. Okay, these are variables. I took some mass somewhere at a distance r, variable distance. So I multiplied mass with the position vector. You have to add such terms, means integrate. Here addition becomes integration by integral dm, which is the total mass. That gives you the center of mass for continuous objects. So once again, what you are doing, you take a small elemental mass dm and found its position r. As this elemental mass moves, the position will change, right? So right now you have taken it as a variable. You will vary it from one point to another point. We will see how, by giving limits to the integral. We'll see all this mechanism. But what I am doing is I took some elemental mass dm and at position r, then I multiplied r and dm, and I have to add such terms, which in this case becomes integration divided by total mass, which is integral dm. Adding all small masses gives total mass. Some people even write this as m, no problem, the mass of the object. But I would like to write like this, integral r dm by integral dm. So for continuous objects, for continuous, I shouldn't say object, system of particles, for continuous system of particles, okay, the definition of center of mass, RCM, is given by integral RdM by integral dm. Again, this is a vector equation. Please note this. This is a vector equation, and I can split it into three scalar equations along x, y, z. So I can write x coordinate of center of mass is integral x dm by integral dm. Similarly, y coordinate of center of mass is integral y dm by integral dm. Z coordinate of center of mass is integral z dm by integral dm. This way you can get individually the x, y and z coordinates of center of mass of this continuous group of particles where there is no gap and all these particles make a body. Okay, so these are our two fundamental definitions. So I've given you two fundamental definitions. One definition is for a discrete system. This is how you calculate center of mass of group of particles. And on the other hand, for a continuous system, this is how you calculate the center of mass of group of objects. Now, let us calculate the center of mass of different kinds of objects. One thing I will tell you where you can avoid integration, if it is a regular symmetrical object with uniform mass distribution, center of mass is at geometrical center of the object. We need not even integrate. Sometimes we can do this. So if the object whose center of mass we are calculating, if it is a regular symmetrical object, nice geometry, nice shape, regular, okay, and uniform mass distribution, you should not have one place more mass and other place less mass. That will make it non-uniform. So if it is a regular symmetrical object with uniform mass distribution, center of mass at geometrical center. Let's see some objects. If you take a ring, it is a regular symmetrical object. So if mass is uniformly distributed, center of mass will be at the center of the ring, geometrical center. Or if you take a disc, again regular symmetrical object, suppose uniform mass distribution, center of mass will be here. If you take a square plate, center of mass will be here. Okay, even for a square wire frame it will be there. Rectangular plate, center of mass will be here. Okay, rectangular plate. So in these cases we need not integrate. Even if you take coordinate axis and do integration, you will get at the geometric center. So sphere, for example, hollow sphere, uniform center of mass is here. Sphere, hollow. Even solid sphere, uniform solid sphere, center of mass is at geometric center. So I'll write CM here and here. So regular symmetrical objects with uniform mass distribution, center of mass is at geometrical center. If you take a triangular plate, it will be at the centroid, median intersection. Triangular plate, uniform plate, center of mass will be at midpoint joining line, median, so this centroid, that will be center of mass. So for all these standard objects, it is a geometric center. What about cylinder? Again, hollow cylinder or solid cylinder, center of mass is here only. Okay, this is very standard. Even if we integrate, we get it. Or rod, for example. If you take a rod, center of mass is at geometric center. We can derive all these integrations, but I'm not doing, just giving you the result. What about if the object is not regular? So let us see some examples. Example 1. Suppose I have a wire frame which is semicircular in shape. Let me first draw a circle and erase one half. Yeah. This makes sense. Suppose this is a semicircular wire of radius r. I don't know why my pen is hanging. Okay. Just 1 second. Okay. So it's a semicircular wire. I want to find its center of mass by integration. It's not a regular object. See, if it was a complete circular wire, of course uniform, center of mass is at geometric center. But now what you have done, you have removed this half. If you remove some mass, center of mass will shift to that side where there is more mass. So it would have shifted up like this. The center of mass will be here. For complete circular wire, center of mass is at geometric center. But if you remove one half, it will shift to the other side. Same holds even for a disc. Suppose this is a disc. Okay, this is a disc. Center of mass is at geometric center. But if you were to cut the disc into two halves and throw away one part, then the remaining this center of mass will shift to that side where there is more mass. Previously it was here at center. Now it will shift up to some location here. That is the new center of mass. So similarly, in the case of our semicircular wire, okay, the center of mass will shift up. So we have to find it. So center of mass will be somewhere. So I'll take this as y-axis. So center of mass is on y-axis. Radius of this semicircular wire is r. How do I find it? How do I calculate it? I have to do integration. Now look at this. I'll explain this integration. We have to chop this semicircular wire into many particles. Then take mass of each particle, multiply it with its position. Then add all such terms, divide by total mass. Here I am interested only in y coordinate of center of mass. Why? You see this formula, y coordinate. Why? Because when you remove the lower half, center of mass shifted up along y axis. So I am interested only in y coordinate. Okay, I am interested only in y coordinate. So what I do, I should take an element. How you will take? See, whenever you are taking an element, you will use some variables, x and dx, or y and dy, or theta and d theta, something like that. So variable and d of that variable, x and dx, both you have to bring into picture. And when you change this x from some initial to final value, you should cover the whole object. For example, if I take a rod, suppose I want to take element on the rod, I take at a distance x a small portion of the rod of length dx. Okay, sorry, a small portion. I don't know why it is hanging a bit. Just 1 minute. So at a distance x, I will take a small element dx. So my dx is after distance x. X is a variable, dx is a small change in that variable. So to cover the, so this dx is my particle, small particle, because particle should have zero size and dx has zero size almost. How do I cover the whole rod? By giving values for x. If x is 0, my dx is at this end. Then if x is L, my dx is at this end. So x takes all possible values from 0 to L. So that my dx is after 0 also, after 0.1 also, after 0.01 also, after 0.2 also, after 1 also, after L by 2 also, and at L also there is dx. So I cover, so as I change x, the dx moves. So I should take an element in such a way that by giving limits to the variable, I should cover the whole object. In the case of a rod at a distance x, if you take a small length of the rod dx, then as you change x, dx moves. X is a variable, right? So if x is 0, dx is at left hand. If x is L, dx is at right hand, and so on. Now, in the case of semicircular wire, how do I take a variable and a d of that variable so that I cover the whole object? You cannot take in a linear way because it is circular. So at an angle theta, I will consider a small portion of the semicircular wire which subtends d theta. So you see this big portion was subtending theta, and after that big portion there is a small portion shown in yellow color which subtends d theta. So this is my element. How can I move it on that semicircular wire? By changing theta. If theta is 0, this fellow will be here. If theta is pi radians or 180 degree, generally we take in radians, that element will be here. If theta is pi by 2, that element is here. So by giving all possible values from 0 to pi, theta goes from 0 to pi. By giving all possible values, I cover the whole object. This is my idea. So in order to integrate, I should choose an element. Element means a part of the object, a small part which is tending to 0. Okay. How should I choose the element? I should choose the element with some variable and d of that variable in such a way that by changing the variable, the element should move and cover the whole object for me. That's my idea. So here I have got the element which is subtending angle d theta. Radius is r. So what is the length of the element? R d theta. That is the length of the element. Okay. And let us say the total mass of the semicircular wire is m. So what is mass of element? Total length of the semicircular wire is pi r. It's got mass m. Total semicircular wire, this one has got a length pi r and its mass m. Then what will be the length of this small portion, the element whose length is r d theta? How is the length r d theta? Radius into angle subtended gives you arc length, right? What is its mass? So I am trying to find mass of the element. First you have chosen the element. Element is small portion of the object. Okay. Then I am finding mass of the element by unitary method. Pi r circumference mass m. R d theta circumference, this is small circumference. What is the mass? So the mass will be m by pi r into r d theta. That is m d theta by pi. You could have also argued in a different way. This mass m is for full angle pi. So what is mass for the small angle d theta? You would have got this. So I got mass of the element. I got mass of the element. I want y coordinate of center of mass of this whole object. So what I should do? Mass of the element, that is dm, I got. What is my dm in my case? It is m by pi d theta. This is my dm. It is m by pi d theta. I got mass of the element. Then what I should do? Mass of the element multiplied by its y coordinate if you are finding y coordinate of center of mass, or you multiply with x coordinate if you are finding x coordinate of center of mass. So mass of the element, that is m by pi d theta. Where is the element? The element is here. What is its y coordinate? What is its y coordinate? This fellow, this fellow. You see, that is r sine theta, because this is r. So this angle is theta. So the opposite side will be r sine theta. Okay. So y coordinate of the element is r sine theta. So mass of the element multiplied by y coordinate, m1 y1 kind of structure has come here. We have to add all such, means integrate, and I should cover the whole object. So I give limits here. My theta goes from 0 to pi. It takes every bloody value from 0 to pi. no exception. Every value that you can think of from 0 to pi. So I'm adding. Integration means to add all such terms. When theta is 0, the mass there into the y coordinate there. When the next angle, the mass there, the y coordinate there. At the next angle again, like that, all contributions I'm adding. If you divide this with total mass, that gives y coordinate of center of mass. Total mass is m only. So I have to do this integration. So my y coordinate of center of mass is what I got previously, integral 0 to pi m by pi r sine theta d theta by total mass. M, pi and r are constants. They don't change. Only theta is the variable. Okay, we are changing theta to cover the whole object. So m, r and pi come out. Bottom m is also there, this m. Integration is only for theta, sine theta, d theta. So this m goes away. So I am left with r by pi. Integral sign is minus cos theta. Integral sign is minus cos. And if you put limits, cos pi is minus 1, minus cos 0 is 1. First put upper limit, minus put lower limit. So you get 2r by pi. So center of mass of this y coordinate of center of mass is at 2r by pi. 2r by pi, it is less than r. Na? So semicircular wire, let me try to draw it properly. This one, center of mass is at a height 2r by pi. It is less than r. If it is r, it should have been here. It's less than it, somewhere here. So this distance is 2r by pi. So center of mass of a semicircular wire is at a height 2r by pi from center. So we got that. So this is how you have to choose an element. You should choose an element using a variable. You can use x dx or y dy or theta d theta. You should use the variable in such a clever way that by giving limits to the variable, you should cover the whole object. That's our procedure. So this is the integration process which we should master step by step, slowly. Okay. First, you should have an idea how you are chopping the object to get elements. Okay. It's a circular wire. So we have to chop it in a circular fashion. So theta d theta is a good idea. If it is a straight rod, x dx. Okay. Or y dy if it is a rod along y axis. So we will see many more integrations. But for a semicircular wire, the center of mass is at a height 2r by pi. Now, look at one interesting problem which I have now, which is a semicircular disc. So the bodies for which I am going to find center of mass with integration are semicircular wire, then semicircular disc. But before that, I'll give you one interesting result before doing semicircular disc. See, suppose I have a square plate. It's a uniform square plate. And suppose I have a circular disc. Okay. And let us say the diameter of this circular disc and the square, the side of the square are same. So what I mean to say is this is A and this is also A. This is a uniform square plate and uniform circular disc. Both are uniform. Let us say both have same thickness, and both are made of same material. Both have same thickness T and made of, actually thickness is not needed. I'm saying same thickness, that's it. And both made of same material. Both made of same material. I have to find center of mass of this system. Now you see, I know for a square plate center of mass is a geometric center here. I know for the circular plate center of mass is at its geometric center here. And I can get the masses of this. How? If I assume density into volume is this mass, density into this volume is this mass. How to get volume? Area into thickness gives you volume. Thickness you can assume some T. Suppose if I know square plate center of mass, I know circular plate center of mass. How to get center of mass of both these together now? So the result says Once you know an object and location of center of mass, you can treat that big object as a point mass at its center of mass. Suppose the square plate mass is m1. Now instead of square plate, I can consider it as a point mass of mass m1 at its center of mass. Similarly, the circular plate, I can consider it as a point mass with its own mass m2 at its center of mass. And then you find center of mass of this 2-point system. How? m1 x1 plus m2 x2 by m1 plus m2 or m1 y1, like that. Discrete system. Whatever you get, that is the center of mass of these two systems. So what I am saying, if a bigger object's center of mass is known, then to calculate center of mass of such bigger objects, you can treat each object as a point mass. Now forget that the object has size. You can treat it as a point mass. But where will you keep it? At center of mass. So what I am saying, what is the mass of the square plate? Let me write it. Density into volume. Volume is a square into t. T is the thickness. What is mass of this density? Same density because same material. And area is pi a square by 4 because radius is a by 2 into thickness is this. So that is the mass. So I want center of mass of the square and circular disc together now. Together. Suppose I take this as my x-axis. Okay. Suppose this point is origin and this point is a comma 0 because this is a by 2 and this is a by 2. I only want x coordinate of center of mass. Why? Because the center of mass will lie on x-axis only. It won't lie on y-axis. Even if you take y-axis, y coordinate will be 0. Center of mass will be on this line. It will be on the x-axis. So it will have only x coordinate. So how to get center of mass of this combined system? The result says, because we already know center of mass of square plate, that is here. So mass of square plate, and you are replacing now the square plate with a point mass at its center of mass. So mass, that point mass value mass into its center of mass, plus circular plate mass, which again you are treating it as a point mass. Where are you treating it as point mass? At its center of mass. So that x coordinate by m1 plus m2. That will give center of mass of both these objects together. Why this will work? Look, I am giving you the proof now. I am giving you the proof. Why my technique works? First, you chop the square plate into m11, its x coordinate is x11 plus m12 x12. You are chopping the square plate into many point masses. So m1n, sorry, x1n, like this, plus circular plate also m21 x21 plus m22 x22. You are chopping it into many particles like this. Finally m2n x2n. So you have chopped square plate also into many particles, circular plate also into many particles by total mass, which is m11 plus m12 plus m21 plus m22, like this, right? I am not using integration here as proof. I am using summation sigma. It is more convenient. This will give center of mass of the square plus circle together. Square plate also I divided, chopped it into many point masses. Circular plate also I chopped into many point masses. I know the x coordinates of each of these point masses. So I'm multiplying mass with x coordinate, mass with x coordinate, mass with x coordinate, like that, adding by total mass. That gives me center of mass. Now look at the clever transformation. I am going to divide this with m11 plus m12 plus m1n, that is mass of square plate, and multiply also with mass of square plate, because multiplying divide is as good as cancelling. Similarly, divide this with mass of circular plate and multiply this with mass of circular plate. Now look at what is there here. This is center of mass of square plate by m11, first particle of square plate, into its x coordinate. So ultimately what you are getting, mass of square plate into x coordinate of center of mass of square plate. That means what is this term actually? You are treating the square plate now as a particle at its center of mass with having same mass. Similarly, mass of circular plate into center of mass of circular plate by what is this? Mass of square plate plus mass of circular plate. See, I proved it. That means if you have a big object and you know its center of mass, another big object and you know its center of mass. Now you want the net center of mass of both these objects, big objects. You can treat the first big object as a point mass at its center of mass. You can treat the second big object as a point mass at its center of mass and find center of mass of this two particle system now. Simple. That will be the center of mass of those two big objects. So I think the proof is now more clear to you. So this is a very important result. This result. So we will next class, tomorrow we'll build on these results, do more complex integrations. So by tomorrow, our integration understanding will come to certain stability. We just started today on this integration of semicircular. Tomorrow, what we will do? We'll find center of mass of semicircular disk by integration, center of mass of hollow sphere by integration, hollow hemisphere, sorry, not hollow sphere. Hollow sphere is a geometric center. Hollow hemisphere, center of mass. Solid hemisphere, center of mass. Hollow cone, center of mass. Solid cone, center of mass. All these we will do tomorrow. I'll conduct in the morning sometime in the class. I'll just message it, maybe 10, 10:30. It's okay, na? 10, 10:30 in the morning tomorrow.
Yes, sir, it is.
Yeah, so we will do that. So that after tomorrow's class, we'll be at a different level in integration. And that will be useful later in rotation and all that. Okay. So any doubts in this? Is it okay, this class?
Yes, sir, it's okay.
Okay, cool. So let me close this.